Coming back to the model, we might want to simplify it to eliminate the variables that are irrelevant. And obviously you can do that by hand. You can call up the model formulation diagram. We'll move this aside so we can see the t-values. You can click and formulate, and then, again, we move that so we can see the t-values. You can then eliminate the ones that have got very small t-values. But there is a problem if you do that, and that is the order matters. That here you might eliminate C2 as the first one, or you might choose Y3, or you might choose Y5, but you only ever follow one path. You'd eliminate, say, Y5, and then something will happen. Let's do that, in fact, and see what happens. Then you might choose to eliminate the next least significant variable. But the order in which you do it might affect what happens to other variables, because all these variables are strongly trending non-stationary time series with very high intercorrelations. But anyway, let's experiment. Let's eliminate the least significant one, which is Y5, and tell it OK, OK, and OK, and it will re-estimate. And we get a smaller model. We've still got insignificant variables, and we could continue in that way. However, there's a better way of doing that, and that's to ask the computer to do it. And what the computer will do is it would certainly eliminate Y5 on one of the path searches, but it will follow a number of different paths. It'll also replace Y5 and start a path from Y4 to see what happens. And then it will replace that and start a path from C2 to see what happens, replace that, start a path from constant, and it will start a path from every variable that is not significant at the probability you required for substantive significance in your model. And I'm going to use 1%, so that will be a t-value of about 2.6. So here you can see the seasonal is just significant at the 1% level, 0.007. So to do that, we'll go back to formulate, and we'll find the previous model. And that's equation 1 with all the variables in it. And that is always remembered. The program will keep a very long list of all the equations you've estimated, and you can save those in due course. Move this back in again for the moment. Tell it OK. And this time, we'll get the program to choose the model, use automatic model selection. As I said, 1% would be a reasonable significance level for this kind of data set. And then we tell it, go ahead, go search. Keep the same sample and forecasts, and off it goes. And it's found the simplest model that it thinks satisfy your criteria. Now, it may be a surprise that in fact it kept C3, which isn't significant at 1%, and it kept seasonal 1, which isn't significant at 1%. And the reason it's kept those is that dropping them makes even more of the misspecification tests significant. Here, the only one that's significant at 1% is the autocorrelation in the residuals test. But if we were to drop these other ones, some of those that are close to significance, for example, the heteroscedasticity test or the normality test, might become significant. And so it chooses a model that keeps variables that aren't strictly significant, as you would call substantively significant, in order to avoid bigger problems down the road. So let's go back and look at the model again. And we'll see we've still got some pretty big outliers. Now, fortunately, there are several ways of dealing with these, and we'll explore one of them in this session. So if we come back to model, formulate, I'm wanting to tell OxMetrics not to select across the variables that are economically important. So we'll highlight all of those, and I want to tell it that they're going to be unrestricted, so they're not going to be selected over, sometimes called fixed. I prefer to call it retained. So we mark all of these as retained variables. So although the program is going to look for outliers and location shifts in the model, it won't select across these. And that will let us set a different significance level in which to select. In fact, I'm going to tell it to choose one. I'll set it in a moment. And we want it to search across whether or not there are outliers, the method of impulse indicator saturation. Now, IIS creates an indicator for every observation. So if you've got 100 observations, it creates 100 indicators. And the indicator for the first observation is 1 for that observation and 0 for all the others. For the second observation, it's 0, 1, and then 0s, the third 0, 0, 1, 0s, and so on. And we're going to enter these in very big blocks, as big blocks as the program feels are possible, in order to find if there are connected outliers or even complete location shifts. So if we click on OK, I want to have a user set p-value, and I want it to use a 0.5% rather than 1%, because we're selecting across roughly 100 indicators, and I don't want too big a chance of keeping any that really don't matter. So if we click OK and OK, the program, you can see, has created all these indicators, and it now begins to search to find which of them correspond to difficult problems in the time series, given that we keep all the economics variables in the model without any question. And it's in fact kept two: 1974 quarter 1, which is the start of the oil crisis, and 1980 quarter 2, which is the trough of Margaret Thatcher's induced Great Recession, when she tried to bring the British economy, as she saw it, back under control. And you'll notice what's happened. All the diagnostics are now insignificant. In other words, some of the diagnostic problems like residual autocorrelation had nothing whatever to do with residual autocorrelation. They were to do with the fact there were big outliers, which then distorted the parameter estimates, which led it to fit an inappropriate model and therefore have residual autocorrelation. If we look at our test results for the graphic analysis and repeat the 4-quadrant diagram, we'll now see that we're not doing quite so well in the forecasts with this model, but we've got rid of the in-sample problem. We're pretty close to normal. There aren't bunches of outliers. They've been picked up by our procedure. Nevertheless, the model that we've still got has got some insignificant variables. So we'll now go back and clear the status of all of these. So here we've kept all of these variables, but now we want to select which of them really matter. So we'll highlight those and then tell the program to clear their status, which removes the U. And now we'll search, but at a more reasonable level, back at 1%, as to which of those matter. And we've already done impulse indicator saturation, so we can switch that off. And now it's come down to a very much simpler model. C1, C4, C5, Y, Y4, C seasonal, and the two indicators. And if we look at the graph, we're doing fairly well. We've still got some problem with the forecasts. This is in fact another recession. You might notice that the data rise very rapidly up to here, and then they suddenly go flat. And if it had continued to rise, you'd expect it to be up here. And this recession follows after the boom of the late 1980s in Britain, following the Finance Act of 1984 that liberated bank and mortgage lending and led to an explosion in lending to households, rather like we've been through with the recent financial crisis and Great Recession. So the lesson could have been learned back here. People borrowed very heavily, and they used the borrowed money not when they took out a mortgage just to buy the house, but took out more than they really needed to buy cars and better furniture, etc. And so we get a very significant boom over this period. Now we can see that using another feature of the power of PcGive and OxMetrics, which is to bring up the graphics menu and fit regression lines